All right, so we're gonna pick up today talking about the collision model. This will be a little familiar. We've mentioned this throughout the unit when we first started this chapter. We've also touched on some of these kind of concepts just in previous units. So this should be a little familiar to you. And so the collision model states that in a chemical reaction, bonds are broken and new bonds are formed. In order for the reactant bonds to be broken, we have to have our molecules collide. Don't think that you just magically mix chemicals together, and once you mix them together, then we magically get a reaction. It's not how it happens. And so when we look at our chemical reactions, we need our molecules to collide if they're going to react with each other. We need them to come in contact with each other. So molecules can only react if they collide with each other. And so this is kind of the collision theory or the collision model. Now, with those collisions, two things have to be true about those collisions. The collision must occur with the correct orientation and with enough energy. And why do we need energy? Well, we need energy because we need them to be moving fast enough in order to break the bonds that are holding the reactants apart. If they don't collide with enough energy, then no reaction will occur. If they collide and there's not enough energy to cause the bond breakage, then they'll just bounce off of each other and go on their way. Or if they're not at the correct orientation, and I'll explain that more in a second, but if they're not at the correct orientation, then we don't have the right collision, so they just bounce off of each other and nothing happens. And so we look at this scenario here, looking at what scenario do we want, or what do we mean by orientation? Well, it's how they're positioned in space. And so if we look at our reactants here and our products here, so we want to make it to where the two green spheres are together and then the blue and red are together. Well, if we look at our reactants, what we're starting with, we've got to get this green to break off. And so this is the orientation, or this is the collision that we want to happen. We want the two green spheres to collide together. If the two green spheres collide together and there's enough energy to cause this green one to break apart, then the reaction will occur and we'll form our products. However, if the two green spheres were to collide together, but there wasn't enough energy for that to happen, then they would just bounce off. And you should remember that the energy required to get a reaction to start is called activation energy. And we'll look at that more here in a second. Let's say you have enough energy, but let's say the green, instead of colliding with the green, it collides with the blue or collides with the red. Nothing will happen because that's not the correct orientation. They'll just bounce off. So remember, when we talk about our collisions, we need the correct orientation and the correct amount of energy in order for that reaction to occur. So there's a minimum amount of energy required for the reaction to occur, and that's called the activation energy. Now, you should probably have heard this term at some point. When we look at this scenario here, if we were to, if you ever played putt-putt or you ever been golfing, if we want to get the ball up and over this mound, then we've got to put in a certain amount of energy to get it up this hill. Now, once it gets up and once it gets over, then the reaction will occur, or the ball will continue to roll down. If we put in energy and you get it up to right here, it's going to roll right back down. So even if we put energy in, we still may not get a reaction. We've got to put enough energy in to get it over the hump, or we have to overcome activation energy. And so that same thing is true with our chemical reactions. If they don't possess enough energy to overcome the activation energy barrier, the reaction won't occur. And so there can be energy present, there just might not be enough energy present in order for the reaction to occur. And we can diagram these with reaction coordinate diagrams. Don't stress, too much. I'll explain these and just the important things we need to make note of. And so we can look at this. You start over here with your reactants. You end over here with your products. And so the one thing to note is the distance from your reactants to the top of the peak. That's your activation energy. So reactants to the top of the peak is your activation energy. Just note here, this activated complex, all this is we form an intermediate. We form a molecular compound that goes in between the reactants and the product. So it's not a reactant, it's not a product, It's just an intermediate. And so we call that the activated complex. And the activated complex is formed at the peak of our graph. And then we see overall change in energy is just the difference in energy from your reactants to your products. And what we see here, and I'll go into this more in a second, this would be an example of an exothermic process. Your reactants are ending with less energy, or your products are ending with less energy than your reactant started with, so it had to release energy overall, so it's exothermic. Just be familiar with these graphs, but don't worry too much about them. In the next slide, we'll talk more in detail what you need to know. So this slide kind of just highlights different things that I kind of highlighted on the last one. This is the activated complex, or you'll see it referred to as the transition state. We're transitioning from the reactants to the products. We have our activated complex that's formed at the transition state. And then this energy gap between the reactants and the peak of your graph is your activation energy. So be able to identify your activation energy from a graph. This is kind of what I would, add this to your notes. This is not in the PowerPoint I gave you. I just added this in. So I would pause the video, take a picture of it, put this in your notes. When we look at these graphs, it's important that you be able to identify an endothermic or exothermic graph. Remember, exothermic is releasing energy, endothermic is absorbing energy. So exothermic reactions, energy is released. Endothermic reactions, energy is absorbed. And so what we see here is we see that the reactions are starting with a higher amount of energy and the products are ending with lower energy. The only way for the products to end with lower energy is for energy to be released. Looking at our endothermic graph, your reactants are starting off low, your products are ending high. So the only way for the products to end with more energy is for energy to be absorbed or energy to be put in. We see the activation energy is the distance from the reactants to the peak. The distance from the reactants to the peak, that's the activation energy. So what you should see here is you should see that the endothermic graph is a lot bigger activation energy. And when we think back to spontaneity, spontaneous processes, endothermic processes tend to be not spontaneous. And that's because they require a lot of energy to be put in for it to occur compared to an exothermic reaction. And so we think more so exothermic reactions are more spontaneous because they require less of an input of energy. You got to put some energy in, but then the amount of energy you get back out is greater than the amount of energy that you had to put in. Here, you got to put energy in. You get some energy back out when the products form or when those new bonds form, but you don't get as much energy out as you had to put in. So make sure you're familiar with these graphs of endothermic versus exothermic. And so here you can just kind of look at temperature. How does temperature have an effect on the reaction? So we know that temperature is the measure of kinetic energy. The higher the temperature is, the more kinetic energy our molecules have, meaning the faster they are moving. And the main thing to see here, we'll go over to this next slide. The main thing, so as temperature increases, the curve flattens or the curve broadens. Thus, at higher temperature, a larger population of the molecules have more energy. The main thing to point out here is looking at blue versus red. The blue, so we look at the area under the curve. The area under the curve just represents the fraction of the molecules that can overcome activation energy. As you increase the temperature, this area under the curve becomes greater and greater, meaning more molecules, a greater fraction or a greater percentage of the molecules have more energy, so they have enough energy to overcome activation energy. So when we look at this, all this is showing us is that as temperature goes up, the number of molecules that can overcome activation energy goes up, therefore the reaction will go faster. If you add more energy in, all you're doing is causing more collisions to happen. The more collisions you have, the greater chance you have of having the right collision, right orientation, right amount of energy. So remember, the speed of our reactions is always going back to collisions. How are we changing the collisions? So when you increase the temperature, you're increasing the speed. You get more collisions. You get more of the collisions what I would say more of the right collisions. And when I say right collisions, I'm just meaning with the correct orientation and the correct amount of energy. So as a result, the reaction rate will increase. So main thing here is as temperature goes up, the rate of the reaction goes up. It gets faster. One thing to note, if you ever see something about the Arrhenius equation, you can look it up. AP doesn't require you to know how to solve it, so we will ignore it if we see it. I've tried to make the practice questions so we don't look at it, but just make note of that if you're reviewing on other sites. And we'll pick up with the reaction mechanisms probably week after spring break.